Hi, I'm Riley, and this is the Transport and Logistics case study, and I'm doing the introduction. The goal of this case is to study and analyze the given data to find where our strengths and weaknesses are throughout the logistics company. At first sight, the data may seem to be very overwhelming. However, with the help of R and Excel, we're able to simplify the data so that it is easier to understand. Using the exact definition from R's website, R is an open source programming language and software environment for statistical computing and graphics that is supported by the R Foundation for Statistical Computing. The R program is widely used among statisticians and data miners for developing statistical software and data analysis. Polls, survey of data miners, and studies of scholarly literature databases show that R's popularity has increased over the past few years. With this understanding, we're able to not only analyze our data, but we're able to dive deeper into the cause and effect of our data. Without visiting any of these locations or contexts that can allude towards the cause of delays, our group has taken some basic assumptions as to why the logistics company is experiencing delays. We will focus on 3 individual legs and then group them together at the end with the outgoing leg. Next to speak will be Timur on leg 1.
Hi, my name is Temur Sati, and then I will be discussing the few initial steps, how we were able to do this project and what we did. The very first one we did was we read our CSV file into the R, and then we also named it the data, just so that we know what's the name. And then the second step we did was we also measured how many shipments were produced in each single leg. And then before they hit the outgoing leg, we also focused mainly on the individual leg for this project. Besides that, we found that not every leg produced the same amount of shipment too. And then the most shipments come from the leg, probably 1, 2, and 3 respectively. Each single leg, we were also able to find how many hops or transportation each product took within the leg. The more hops a product takes, the more delays the shipment is susceptible to obtain. Leg 1 also has the most shipment and has the most hops in each single category. If we ratio it, that's over 1/3. If we could find a way to reduce the number of hops per shipment and create the direct routes, we could in turn reduce the number of delays. Each shipment would be vulnerable to.
Hi, my name is Whitney, and the next part we examined the planned or estimated times for each stage in the legs and compared them to the effective or actual times the shipments took. By doing this, we subtracted the actual from the planned, and if we got a negative number, a delay would have occurred. Next, we changed all of our delays or negative numbers into yeses for the delays and no's for being either on time or ahead of time. We now were able to count how many delays were in each check-in, departure, freight reception, and overall delivery within each leg. We found the bottlenecks in each leg and found which legs were creating the most delays. The first departure stages in each leg is the bottlenecks of the legs. We found the most delays in leg 1 with a total of 6,366 delays, then leg 2 with 4,236 delays, then leg 3 with 2,191 delays, and finally the outgoing leg has 7,456. This is probably because of the amount of shipments that could even produce a delay. Since the outgoing has each shipment from all the legs, the outgoing leg should have the most delays available.
I'm Andy, and I will be going over the classification. After viewing each stage in each leg, we found out that the departures held the most delays, so that's where we tried to focus our classifications. We created this system that finds out how many delays were at each severity. We used an early classification, a late, which starts the delays, so from 1 minute delay to 119 minute delay. The really lates were 120 to 479 minutes. Super late were 481 to 999, and 1,000 or longer was considered an ultra late delay. The diagram here shows that we ended up having 539 ultra late times. So that's actually 16 hours, or 16 days and 16 hours late. So that's over 2 weeks, which is kind of So I should say. Once we found the delays in each category, we subtracted backwards to find out how many delays were between each classification. So we took this 539 minus, we have the 1541 minus the 539, and that tells us we have 1,002 super late, and then we repeated this process again and again, and we ended up with 1,120 really late, 750 late delays. And then we repeated this process for each leg. Not only did leg 1 have the largest number of delays, but it actually has the relation to the longest delays as well. Leg 2 had 373 ultra delays, leg 3 had 189 ultra delays, and then the outgoing holds the most because it has to coordinate all the other legs coming into it, which had 682 delays, but that's understandable. Next, Luke will talk about the regression models.
My name is Luke Ronsberg, and I'll be talking about the regression part of this project. As a group, we decided to use the pairs and panels regression models for our data to help us analyze the data as well as to help give us a visual representation. We focused on each individual leg's departure one as well as the delivery segment because we learned through R that most of our delays came from these two spots respectively. As these graphs show, we have all of our data on a scatter plot as well as a bar graph. Looking at the scatter plot, each black dot represents a time and a place. And if you look at the graph, you can see that a large majority of these points are slight delays or slightly on time. A few black dots are farther down the graph, which shows our outliers or the more costly delays that we have. The bar graph shows the amount of delays in terms of quantity. The most times are either on the 0 mark, which are slightly before or slightly after. And if you look at the graph more, there are no bars representing the longer delays because there was not that many in terms of quantity.
All right, and I'm back for the conclusion. As a group, we found that leg 1 was the worst leg, had the most delays out of all of our individual legs. But however, the outgoing leg had to congregate all of these legs into one shipment. So it makes sense that that one had the most delays and the most severe delays. This is where we found our bottleneck. Everything has to go through our outgoing leg, and therefore 1, 2, and 3 caused the outgoing leg to have the most delays. We had a couple ideas to help fix some of these problems. One of them was reducing the amount of hops between our routes and our shipment points. Doing this would basically decrease our variability of delay and help us shorten up our shipment times. And then by eliminating our number of hops, we're basically taking it so that we're going from point A to point B directly, and therefore we are creating less delay by eliminating hop points. At this point, we have all of our references, and we'd like to thank all of our references for the information that we collected from them, and that is our conclusion.